Can you see the material?
Yes, ma'am.
Is it legible?
Yes, ma'am.
So, the name of this course is Linear Control Systems, right? So, the category of this course is Program Core. Lecture tutorial breakup is given. You should not be bothered about this breakup. And this is the detailed syllabus. And the syllabus is also available in the university website, I guess. These are the list of textbook as well as reference book. Nice, Nagrad Gopal, Puo, M. Gopal. There is a book by D. Roy Chaudhary that is also a very good one. Now you must learn the course outcomes. I guess you have heard this term, course outcomes, CO. So whenever we will be interacting, please unmute your device one at a time, right? And make the session interactive. Have you heard this term, course outcome, or in short, CO?
Yes, ma'am.
So please do respond, right? So the COs are like this. We'll have to learn the COs because at the end of the after finishing the course, so at the end of the semester, we'll be asked to provide course end feedback, and course end feedback is based on the COs, coverage of COs. So the first CO is like this: after finishing the course, the students should be able to explain the configurations of control systems, the notion of stability, and related concepts on steady state and transient errors, disturbance reduction, insensitivity, and robustness. Right. So today, in in this particular class, we'll try to learn the notion of stability. What is the stability concept? Now, the second CO is the students should be able to describe different control system components, interpret time responses of the systems, should be able to discuss about the absolute stability of a system using Routh-Hurwitz criteria. Now, the students should be able to develop, this is the third CO, CO3, develop knowledge on block diagram reduction technique and signal flow graph, should be able to develop knowledge on closed loop frequency response of an LTI system. The full form of LTI system, I guess you know because already you have done a course on system theory. So the full form of LTI system is linear time invariant system. Now, CO4, the fourth CO, uh, is the student should be able to design suitable PPI, PD, PID. That means proportional, proportional integral, proportional derivative, and proportional integral derivative controllers. And should be able to examine the dynamic behavior and stability of an LTI system by constructing root locus and should be able to ascertain the stability of a system using Nyquist criterion. And the last CO5, the student should be able to analyze, it should be it should not be and. The students should be able to analyze LTI system and synthesize controllers for the same using state space technique Should be able to design suitable compensators using both frequency and time domain based techniques. Right now, I'll be covering the second part of this course, part two. And so we'll start with the notion of stability, right? Then we'll learn Routh-Hurwitz criteria, which is basically a stability judging tool for a linear system. And one very important thing is, from the name itself, it's clear the name of the course is Linear Control System. So, from the name itself, it's clear that in this particular course, we'll only consider linear systems. Not only linear systems, linear time invariant system or LTI system. So, in this course, there is no scope to discuss nonlinear systems or discrete systems or linear time varying systems, right? And also, we know, try to recall that since we'll be discussing about linear systems, hence, from the from the very beginning, we should keep it in mind that a linear system always obeys law of superposition and law of proportionality. So we'll be using those two laws because we will be considering only linear system. And within the purview of this part, as I told you, Routh-Hurwitz criterion, that means in this part, actually we'll try to ascertain the stability of a linear system, linear time invariant system, right? So we'll be studying quite a few stability ascertaining tools which are applicable for linear systems only. So such tools are Nyquist stability criterion, Routh-Hurwitz stability criterion, right? And some other design and analysis tool we'll be studying, which are also applicable for linear systems like root-locus technique, block diagram reduction technique, signal flow graph. And finally, we'll learn how to use state variable technique, which is basically a time domain based technique. So, state variable modeling technique, how to use that particular technique for modeling and analysis as well as for designing of controllers for a linear time invariant systems. So COPO mapping, you can, I don't know whether you are aware of all those POs, I don't know. So for the time being, you can leave it. So linear control system part 2. So this is module 1, basically chapter 1. This is the first chapter. And the chapter title is like this: Concept of Stability, Notion of Stability, Algebraic Criterion, and Routh-Hurwitz Stability Criterion. So this is my email ID. I do have another institutional email ID which you can note down, because from that particular email I shall send you the meeting links. So you can note it down: madhubanti.moitro @Jadavpur University .in. madhubanti.moitro @Jadavpur University .in. The mail from which you have received the meeting link. Now, I used to teach this subject because this is a mathematical one. I used to teach the subject using chalk and board technique. But since for online classes, I can't use chalk and board. That's why I've prepared a handwritten note for you and I've tried to detail down all the theories that we're going to discuss. Okay. And I guess it's quite legible. Is it legible?
Yes, ma'am.
I guess. Let's make it full screen. Okay. So first chapter, concept of stability. Now, concept of stability, the notion of stability is always associated with a system, right? So that means given a system, the first task as system engineer or control system engineer that we do is to judge whether the or we decide or try to ascertain whether the system is a stable one or not, right? So first of all, it's required to learn the definition of a system. So since you have already studied system theory, please tell me a few formal definitions of a system. How do we define a system?
A system is something that takes some input and shows some output.
Okay, I accept this definition. That means if a system is excited with some signal, that means if some input signal is given to a system, the system will be able to produce some signal. Now, the system is designed or devised to perform certain tasks, right? So, if a system produces or generates any kind of signal, that is not acceptable to us, right? So, if we give an acceptable form of input to the system, or in other words, we can say that we some form of command is given to the system. That means the system is being asked to perform certain tasks, and accordingly the system should be able to generate a response which will follow or which will be in accordance with the input command. In terms of signals, the system should be able to produce, should be able to generate an output signal which will be able to follow the input signal. So that is the purpose of a system, right? So if we find that we have given a bounded input to the system, a bounded input to the system, and if we find that the system output is going on increasing towards infinity, right? So the system, or in other words, the output of the system is unbounded, completely unbounded, that means will not be able to work with that particular system. Why? Because the output signal is not following the input bounded signal. The output signal is not bounded at all, right? So we'll not be able to work with that system. Our purpose will be defeated, and hence, in that particular condition, we'll will classify the system as an unstable one. Do you get my point?
Yes, ma'am.
Now, in earlier days, if a system was excited with a bounded signal, and if it was found that the system did exhibit undamped oscillation at the output, undamped oscillation at the output, then the system was considered to be an unstable one. But this consideration, this notion is not a very clear one. or not a bit, or in other words, it's not a very accurate one, right? So we'll have to judge the, or we'll have to understand the notion of stability of a system in a detailed manner. So, roughly speaking, again, if you try to explain the stability, the notion of stability of a system in an informal manner, then we can say that the stability of a system implies that small changes in the system input, in initial conditions, or in system parameters. That means if you slightly change the system input, or if you slightly change the initial condition, or if you slightly change the system parameters, the output response of the system should not deviate farther and farther from the input signal, right? So, what is the bottom line? The bottom line is the system should always be able to follow the input signal. Uh, if you find any difficulty, if you do have any question or query or any doubt, feel free to interrupt me and feel free to ask the question. Okay. So, moreover, stability is a notion that describes whether the output can follow the input command, and obviously an acceptable input command will always be bounded in nature, or whether the output gradually deviates farther and farther from the input. So the first condition is a desirable condition where the output response can follow the input command, and under such situation the system will be classified as a stable one. And in the second case, if the output signal gradually deviates farther and farther from the input signal, then the system will be called or will be considered to be an unstable system. Now, typically we can classify the control problems, or we can classify typical control problems into two groups. The first one is a regulatory kind of a problem. The second one is a tracking kind of a problem. So, what is the difference between these two? In regulatory kind of a problem, the input command or the input signal to the system is kept fixed, right? It's often called the reference input or set point. Reference input or set point. So, let's take one example. So I guess if you consider the example, then it will be easier for us to understand what is a regulatory kind of a control problem. Suppose you want to control the temperature of a room. Say you want to maintain the temperature of a room at say 25 degrees centigrade, right? So if I consider the entire system to be a box, like a box, then the input signal or input command to the system will be 25 degrees centigrade, right? And the controller within the system should act in a manner such that the output or the actual room temperature is maintained at 25 degrees centigrade, right? So in this case, you see the input signal is constant, is fixed, that is 25 degrees centigrade. Okay. Now, in contrast, in tracking kind of a problem, the input command may not be a constant. The input command itself can vary with time. Just consider a missile control system, or a flight control system. At times, often, what is done, the desert trajectory, or flight path of the missile is embedded into the computer of the flight control system. So since it's a flight path, that means The path will vary with time, will be a function of time, right? So that means the input to the system is not fixed, it's a function of time. And accordingly, depending on the input trajectory, it's expected that the flight control system should be able to follow that particular pre-specified or predefined flight path. That means the system should be able to generate signals or able to generate a flight path which will which will be in accordance with the pre-specified flight path. Clear? Now let's come to this diagram. So typical control problems, as we have seen, regulatory kind of a problem and tracking kind of a problem. And as we have discussed, you see in the first case, the input command or the input signal is constant, like this, right? So this is the input signal, right? And it might so happen that if the room temperature was lower than, say, 25 degrees centigrade, then because of the presence of the controller, the room temperature will start increasing, and finally, after a while, you see that the output temperature or the actual temperature of the room, or basically the output response of the system, is converging with the input signal given to the system, impressed upon the system, right? So if the temperature of the room was above 25 degrees centigrade, then for a stable system, can you follow the cursor?
Yes, ma'am.
This is the cursor. So the variation of the output signal would be like this. But since after a while, you see, the output signal is converging with the input signal, right? That means we can say, yes, finally the temperature of the room will be maintained at 25 degrees centigrade, and hence the system is a stable one, right? Instead, if it happens that the output response, because of the malfunction of the controller, or there could be some other reason as well, if we find that the output temperature or the actual temperature of the room is increasing increasing in this particular manner, that means it's as time t increases, the room temperature is increasing farther and farther and deviating from the input signal. Can you follow the cursor?
Yes, ma'am.
That means
Yes, ma'am.
that means that it's obvious that the temperature of the room cannot be maintained at 25 degrees centigrade, and moreover the temperature is increasing, which is dangerous, right? So that means this is not a desirable situation, and hence the system will be called an unstable system. Clear? Now let's come to the tracking problem. So suppose this is the input trajectory, pre-specified, predefined trajectory. And if the missile actually follows this path, which is again converging with the input trajectory after a while, then the situation is pretty acceptable to us. And we can say that, yes, we can work with this particular system, right? And we can say that the system is behaving like a stable system. Right? Instead, if the output trajectory is something like this output trajectory, right? Or something like this, right? That means the actual missile will not be able to follow its pre-specified trajectory, and it might hit some different target, and that might result in a catastrophic situation. Okay, so the system is not a stable one, and We cannot work with that particular system. So, as I said, why we are so concerned about the stability of the system? Because from the previous discussion, intuitively, I guess you can understand that if a system is not a stable one, then the system is completely useless. We cannot work with that particular system, right? The system is absolutely meaningless to us. Okay, so let's take one example, another example. Suppose, um, let's consider this class. Okay, so suppose I give you a command, any student, or if I ask any student to lift a heavy load. Okay, and suppose the student is not doing well, he or she is not feeling well, God forbid, he or she is feverish, then what may happen? While he or she will be trying to lift the load, he or she may start trembling. That means some sort of undamped kind of oscillation. And still, if he wants, or if he or she wants to lift the load in the process, he or she might collapse, right? So, if we associate, or if we analyze this example, then from this analogy, we can argue intuitively that even an unstable system may break down, right? If the output signal goes on increasing and increasing, and if the output signal is unbounded, at times think of a moving system, so a DC motor with having a flying path, right? So, if the system is not stable, so in the extreme condition, it may so happen that the system will break down, which is not desirable at all. And hence, stability aspect is of a system is so very important, because again I'm reiterating that if the system is not stable, the system is absolutely useless. We cannot work with that particular system, and the purpose for which the system has been designed will be completely defeated. So far, have you understood? Do you have any question?
No, ma'am.
I can see this point, which is written over here. In a non-rigorous manner, a system is said to be unstable if its output is out of control or unbounded, even for a given bounded input. So we conclude that if a system is unstable, we, the control system engineers, or simply the system engineers, cannot make the system functional. So, what is the task of the system engineers or control system engineers? The first task is, given a system, the first task is to find out the stability of the system, right? To judge the fact that whether the system is a stable one or not. If the system is a stable one, fine.